A lot of pop science outlets give a certain summary of quantum computing that I can almost guarantee leads to misconceptions. The summary goes something like this. In a classical computer, data is stored with bits, some sequence of ones and zeros, but in a quantum computer, you are able to represent every possible sequence of bits of some fixed length all at once, in one big thing known as a superposition. And sometimes the implication of these summaries is that quantum computers can be faster by basically doing whatever a classical computer would do, but to all of these sequences in parallel. Now, this does gesture at something that's kind of true, but let me see if I can prove to you why I think this leads to misconceptions, and I'll prove it using a quiz. To set it up, I want you to imagine that I have a mystery function, and I tell you that there's a certain secret number among all the numbers from 0 up to n-1, where if you plug that value into my function, it returns true, but if you were to plug in any other value, it returns false. And let's say you can't look at the innards of the function to learn anything about it. The only thing you're allowed to do with it is just try it out on numbers. The warm-up question is, how many times, on average, would you have to apply this mystery function in order to find the secret key? Well, if the setup was in an ordinary classical computer, there's really nothing better that you can do than guess and check. You go through all the numbers, and maybe you're lucky and find it early, maybe you're unlucky and it doesn't come up until later, but on average, with a list of n possibilities, it takes 1/2 of n attempts to find the key. Now, in computer science, people care about how runtimes scale. If you had a list 10 times as big, how much longer would it take? And computer scientists have a way of categorizing runtimes. They would call this one O of n, where that big O communicates that maybe there's some constants like the 1/2, or maybe some factors that grow slower than n, but the factor of n is what explains how quickly it scales as n grows. If n goes up by a factor of 10, the runtime also goes up by a factor of 10. Now, here's your quiz. For the equivalent of this setup, but in a quantum computer, what's the best runtime for finding the secret key? I've asked a variant of this quiz many times in a certain lecture that I've given over the years, and the options I typically offer are O of square root of n, O of log of n, O of log of n, and O of 1, where here O of 1 would mean that the runtime is just some constant that doesn't actually grow as n grows. Now, to be fair, I have not defined quantum computing. In fact, doing so from the ground up is going to be the goal of this video. So without showing you what this mystery function would look like in that setting, it's kind of an incoherent question. But it's not really meant as a quiz that I'm grading you on or anything, it's just meant to be a gut check of intuition before we dive in.